Hello students, today in this session we are going to discuss a new topic, that is organic synthesis via enolates. Okay, so let us see what are these enolates. Before dealing with the enolates, let us see what are these active methylene compounds. See, the class of compounds in which methylene group is directly bonded to electron withdrawing groups are called active methylene compounds. Okay, you know what is a methylene group? This is a methylene group. If this methylene group is attached to electron withdrawing groups, then such compounds are called as active methylene compounds. We call them as active methylene compounds. Let us take an example of this active methylene compounds. So the best example for an active methylene compound is this. Active methylene compounds, in which the methylene group is attached to two electron withdrawing groups here. Okay, this is ethyl acetoacetate. This is ethyl acetoacetate. In active methylene compounds, the hydrogen of this methylene group is acidic in nature. Acidic in the sense it can be easily removed by treating with the strong base. Okay, so this hydrogen can be easily removed, okay, by treating with them strong base. So these active methylene compounds contain an acidic hydrogen and are very reactive in nature. Okay, now the acidic character of these alpha hydrogen is attributed to the following reasons. Let us look at the reasons for this. Let us take a compound containing an active hydrogens. So we have a carbonyl group here. The carbon attached to this carbonyl group is called as alpha carbon, and the hydrogens that are attached are called as alpha hydrogens. We call them as alpha hydrogens. So these are all alpha hydrogens. So these alpha hydrogens are generally acidic in nature. See, oxygen is more electronegative than carbon, so oxygen will pull electron towards itself. As a result, this carbon will acquire a positive charge, so this carbon will pull electrons from here. So this carbon becomes positively charged and this carbon will pull electron from here. As a result, the electron density in carbon hydrogen bond decreases. That means this hydrogen will be weakly held. So hence a base can easily remove this proton. This is the reason why these alpha hydrogens are acidic, because the alpha hydrogens, that means in active methylene compounds, what happens is because of the presence of an electron withdrawing group, the carbon hydrogen bond weakens and this can be easily removed. So it can be easily abstracted. This is the reason why they are acidic in nature. And another reason is after removing the proton, you get an anion. There will be an anion. So the anion formed is resonance stabilized. The anion formed is resonance stabilized. CH2. So this is called as an enolate. We call it as an enolate. Okay. So en because of the double bond. Enolate because of O minus. So this is called as an enolate ion. So these alpha hydrogens are acidic in nature, and another reason why they are acidic is because after removing the proton, whatever the anion formed is resonance stabilized. Okay, so hence active methylene compounds are very reactive and this can be used in synthesis, organic synthesis. Let us first discuss the preparation of this ethyl acetoacetate, okay, an active methylene compound. So synthesis or preparation of ethyl acetoacetate. Ethyl acetoacetate can be prepared by condensation of esters having alpha hydrogen. Esters having alpha hydrogen, when treated with strong base, undergo self condensation to produce beta ketoesters. This condensation is called as Clason's condensation. Ethyl acetoacetate is a beta ketoester. CH3 C double bond O, CH2 C double bond O, OC2H5. Okay, so this is alpha carbon. At beta position there is a keto group, so beta keto ester. So this can be produced by a condensation reactions. The condensation generally involves the condensation of esters having alpha hydrogen. Okay, let us see the preparation of this. Two molecules of esters having alpha hydrogen undergoes base catalyzed condensation. The base that is used is sodium ethoxide. They result in the formation of beta ketoesters. Okay, to prepare ethyl acetoacetate, which ester should be considered? Okay, now, so to prepare ethyl acetoacetate, the molecule used is this CH3 C double bond O, OC2H5. Ethyl acetate is used. Ethyl acetate is used. See, this is an acetate part. Ethyl acetate. Ethyl acetate undergoes self condensation. Okay, I will write another molecule of ethyl acetate. CH3 I will write as this CH2H C double bond O, OC2H5. Ethyl acetate, when treated with base, that is ethoxide, in presence of ethanol, followed by acidification, okay, will give you ethyl acetoacetate. So they undergo self condensation. Resulting in the formation of CH3 C double bond O, CH2 C double bond O, OC2H5. CH3 C double bond O, this goes off, CH2 C double bond O, OC2H5, plus this product, that is C2H5OH. Ethanol is obtained. This is ethyl acetoacetate. Let us discuss the mechanism of this. So this is a beta ketoesters. Generally beta ketoesters are prepared by Clason's condensation. Clason condensation involves condensation of esters having alpha hydrogens. Okay, ethyl acetate as an alpha hydrogen. Okay, hence the condensation of this will give you ethyl acetoacetate. So preparation of this, the mechanism, let us discuss the mechanism of this Clason ester condensation. Okay, so it involves the following steps. In step 1, I will write the ethyl acetate, ethyl acetate. This carbon is attached to an electron withdrawing group. So hence this hydrogen will be acidic in nature. In presence of a strong base like ethoxide ion, what happens is, since this is acidic in nature, this ethoxide ion is a base, strong base, it abstracts this proton. It abstracts this proton and it results in the formation of CH2 minus C double bond O OC2H5 plus C2H5OH, right? So a carb anion is formed. Carb anion is formed. Okay, what happens is, in step 1, this ethoxide ion, what it does, it removes this proton. What it does, it removes a proton. Why? Because the proton is acidic in nature. So the lost proton gets abstracted. When proton is abstracted, a carb anion is generated. CH2, a proton is removed here, you get CH2 minus. In step 2, what happens is, this carb anion that is generated will attack the another molecule of ethyl acetate. Okay, I will write another molecule of ethyl acetate, CH3 C double bond O OC2H5. This is the carb anion generated, CH2 minus C double bond O OC2H5. Okay, so this carb anion negative charge will attack this carbon. Why it will attack that carbon only? Why? Because this carbon will be positively charged. Why? Oxygen is electronegative, oxygen pulls electron towards itself, so this carbon will be positive, so this negative charge will attack this carbon. When it attacks, double bond O gets converted into single bond O minus. So what you get is CH3 C double bond O becomes single bond O minus. Okay, this OC2H5, this CH2 minus attacks this, so it is CH2C double bond O OC2H5. Hope you're getting this. In first step, from one molecule of ethyl acetate, this abstracts a proton, resulting in the formation of this carb anion. This carb anion, it attacks another molecule of ethyl acetate at this site, resulting, when it attacks, one bond should break, double bond O becomes single bond O minus, and the remaining as it is. This is OC2H5, this is as it is. Okay, this is what happens in step 2. Step 3. Okay, this CO minus OC2H5 CH2 C double bond O OC2H5. Right, what happens is, the negative charge comes here, so when a new bond is formed, old bond should break, this goes off because these are good leaving groups. This goes off, resulting in the formation of this compound CH3 C double bond O CH2 C double bond O OC2H5 plus OC2H5 minus, OC2H5 minus, because this is going along with the electron, or C2H5 O minus is what you can write. I repeat, in first step, ethoxide ion removes a proton. resulting in the formation of this carbanion. This carbanion attacks another molecule of ethyl acetoacetate. When it attacks, double bond O becomes single bond O minus. In third step, what happens? This O minus moves here, negative charge. So this bond breaks, resulting in the formation of ethyl acetoacetate. Ethyl acetoacetate. But what happens is, this is not the product that we are going to get. Even though we are expecting this product, what happens is, this is an active methylene compound, and you all know that active methylene compounds are generally acidic in nature. Active methylene compounds are generally acidic in nature. So since active methylene compounds are acidic in nature, and we have ethoxide in the solution, we have ethoxide, and you know the ethoxide is a strong base. So this ethoxide will abstract this proton. This is what happens. Okay, I'll write it as step 4. You are going to get this molecule, but the problem is, the solution has ethoxide ion, and ethoxide ion is a strong base. So this ethoxide ion will remove this proton, because these protons will be acidic in nature. So this is what you are going to get: CH minus, C double bond O, OC2H5, CH minus, and here there will be Na plus in the vicinity. This is what you are going to get. So if you want ethyl acetoacetate, you need to go for acidification of that. Okay, if this salt, if you treat it with HCl, so you need to go for acidification. So what I get? You get this compound back: CH3, C double bond O, CH2, C double bond O, OC2H5. So that is why acidification is necessary. Okay, so the reaction takes place in 4 steps. So what are the 4 steps? In first step, ethoxide ion removes a proton. Carbon ion attacks another, ethyl acetate molecule, resulting in the formation of this. Okay, next the O minus comes here, this goes off, resulting in the formation of ethyl acetoacetate. But ethyl acetoacetate, in presence of ethoxide ion, will be in this form, so hence we need to acidify it to get back the ethyl acetoacetate. So these are the steps that are involved in the reaction. Steps involved. This is called as the Clason's condensation. Okay, so students, hope you have understood what are active methylene compounds and what we mean by this Clason's condensation. Okay, now the next point. The next point is of keto-enol tautomerism. Let us see what is this keto-enol tautomerism. Okay, so ethyl acetoacetate exhibits this tautomerism. Let us see first what is this tautomerism, and next we'll see what is this keto-enol tautomerism. Tautomerism is a phenomenon in which two isomeric forms having different functional groups are interconvertible and can exist in dynamic equilibrium. Keto-enol tautomerism is one of the type of tautomerism. Generally, carbonyl compounds containing alpha hydrogens exhibit keto-enol tautomerism. Okay, for example, so these compounds, see, we have C double bond O. Okay, so this is carbonyl group. The next carbon is alpha carbon, and there is a hydrogen called as alpha hydrogen. So carbonyl groups containing alpha hydrogen exhibit this type of tautomerism. So what happens? So this is called as a keto form. There is a ketonic group. What happens is, this electron, they move here, resulting in the formation of double bond. So a new bond is formed. This goes here. Okay, so this bond breaks, so H plus that is released, it will combine with this. So this is what you are going to get. C, you have C here, these electrons are moving here, so you get a double bond. This is moving here, double bond O gets converted into O minus. O minus will be OH. This is called as enol form. Why it is called as enol? Double bond all is an alcohol. Enol form. Simple example is acetone. CH3CO, C double bond O, CH3, CH3, right? So this proton, this carbonyl carbon, next carbon is alpha carbon. So the hydrogen goes off. Okay, the electron it can shift here. So this is what you are going to get. See, this is how it is there. C double bond O is there. We have CH3. We have the CH. This will move here and this will move this. So what you get? You get CH2 double bond C OH CH3. This is enol form. Generally, keto form is more stable than the enol form. So ethyl acetoacetate also contains alpha hydrogen, hence it also exhibits keto-enol tautomerism. Keto-enol tautomerism. Okay, let us take that example of an ethyl acetoacetate. So this is ethyl acetoacetate molecule CH3, C double bond O, CH2, C double bond O, OCTH5. So this is the keto form. This is the keto form. Okay, what happens here, sir? We have carbonyl group here, and this hydrogen is called as alpha hydrogen. Okay, so what happens is here? The carbon hydrogen electrons they move here, forms a double bond. This moves here, so resulting in the formation of CH3C. Double bond O will be OH. See, double bond O becomes OH. So double bond O becomes OH. There will be a double bond here. CH, C double bond O, OCTH5. This is the enol form. This is the enol form. So in ethyl acetoacetate, the keto form will be around 90%. That means maximum keto form is generally more stable. Okay, ethyl acetoacetate exhibits keto-enol tautomerism. Okay, so keto form, and this is the enol form. This is the enol form. Okay, so ethyl acetoacetate exhibits keto-enol tautomerism. Generally, compounds which contains alpha hydrogens, I mean carbonyl compounds containing alpha hydrogens, exhibit this keto-enol tautomerisms. Okay, so this was about the preparation of ethyl acetoacetate, the tautomerism of ethyl acetoacetate, and the definition of the active methylene compounds. Thank you.